All right, so one, I need to clear something up, I think. I think I misspoke. I didn't go back and look at the videos, but I believe I did. So if we want to, let me go to this thing. There we go. If we want to say that gamma is G homotopic to 0, I think I implied that 0 had to be inside there. It doesn't, okay, because I was kind of pointing things in like this. I want to be clear that it doesn't have to be inside there, but I started thinking I probably implied that. In that, or who knows, maybe I even said it, but because if you take any map gamma, and so that's some path, some parameterized path, so gamma equals x of t plus I y of t, then using that the convex combination thing, I can always make this go nicely and continuously to the point 0 or any other point, because again, all I have to do is take, for each of these values of t, use 1 minus s times gamma, and as as s goes to 1, this goes to 0, right? So the x, so h, I guess we'll call it, because that's it. As s goes to 1, then h goes to the point 0, and so it could be, you could have it like that, and in which case everything's shrinking down toward it, but yeah, it doesn't have to be inside it. So oh, that wasn't coming up. Did we lose connection? Oh, we'll try that again. Let's see. It's thinking, maybe. Okay, well, let me go here and we'll oh yeah, start broadcasting. Okay, now what happens? Maybe I have to reopen it. So reload. Yeah, it's there now, right? Yep, awesome. Okay, so I lost you there at one point. All right. So the gamma contractible to 0 or any other point. The idea is that you've got something like that, and if you take 1 minus s times that and just that, then as s goes to 1, this h will go to 0, and that's the point 0. Now though, you could but it could be out here and do that same thing, and any other point, what you would be doing would be using your h. You would take the 1 minus s gamma and then plus s times your other point z naught. And so as s goes to 1, again this disappears and you just get z naught. Okay, so took care of that and we got this thing connected again. Alright, and so what's left, we just want to talk about the generalized theorem, and I might go look at one question because that kind of intrigued me at first, and now it doesn't so much, but you'll see why. Okay, so we need to talk about the inside, outside of a simple closed path. So, first of all, it's simple. It never crosses over itself. So that is not simple. That is simple. Closed, yep. It ends up like that. It can't be something like that. And then a path, well, yeah, it's a path. So, okay, get rid of those. And that's a simple closed path, and we want to talk about being on the inside. And what we'll say is it needs to be positively oriented. So inside or interior, and here they talk about a piecewise. Oh gosh, I didn't go back to that. Okay, try that again. Sorry. Inside and outside. So if I go back here, we're looking at inside, outside. Okay, we have a simple. Okay, that means it never crosses itself. So like that's not simple. Closed. Well, it wasn't closed either because the two endpoints didn't meet. And then a path. And so, something like that is just fine. Simple closed path, we want to talk about the inside and the outside. Now, that has to do with orientation. So let's go look at their thing here, their definition. So a piecewise smooth, simple closed path is positively oriented if it is parametered so that its inside is on the left as our parameterization traverses gamma. An example is a counterclockwise oriented circle. Right? So we've got, we're going to do this if I'm going counterclockwise on this, then the interior is to my left as I go. Put yourself on that path, and that's to the left. So this is positively oriented. And so if I had gone this way around, there's still the interior, then this would be negatively oriented. Okay, so we get to this very generalized Cauchy integral formula. And let me go back and show the negatively oriented. So there was positively oriented going around that way, things are to the left. Negatively oriented goes around clockwise in this case, and that makes the interior to the right. Okay, I'm having a little trouble here. So we've got F is holomorphic in a region. Gamma is a positively oriented, simple, closed, piecewise smooth path. So a bunch of things such that W is inside gamma, and gamma is contractible to 0. So it can head to some point, any point, as we pointed out. Okay, then we have this nice theorem, which is pretty much the theorem you saw before, except now this is just some gamma. It no longer has to be a circle. And that's all theorem 4.27 does. Okay, it just says, oh yeah, but we've got to think of it as being positively oriented and all that kind of stuff. And yeah, so here they just use a general gamma to make pi, because we already saw that if we used a circle, we would get pi for this. Okay, so that gets us down to the exercises. And you know, the exercises I'm going to have you do are a lot of these calculation problems of computing lengths of paths here first. Yeah, that's a good thing. And then, you know, a lot of these integral problems. And let's see, which one? Yeah, so where is it? Oh, right here. So 414, this kind of intrigued me because you know, when I first saw this, let's go back. So this is find a path so that this would be 2m pi, 2m pi I, and so yeah, we want to find gamma so that 1 over z dz is equal to 2m pi I. Well, I looked at that and I thought, well, that didn't make sense to me at first, because what I know is any of these paths. So if this is 0, you know, any of these paths, we've got our theorems, they all yield 2 pi I. And so I'm thinking, well, how could you possibly do that? And then it hit me. And if we go back to the problem, the one difference here is generalizing these, you know, so that find a closed path, not simple. Okay, and so in that case, if it just has to be closed, then pick any one of these and make it a circle, I guess, and go around m times, and then, you know, if you do that, then your parameterization becomes you know, integral from like 0 to 2m pi I, and you know, say we use the unit circle, so that was e to the it, right? So we would have our 1 over e to the it, then times I, e to the it, because of the derivative, dt. Well, of course those cancel and you just get I, and oh yeah, there's 2m pi I. So yeah, it kind of intrigued me, you know, and at first, because I thought, that seems to be contradicting what it didn't say simple. And that's the thing, is simple, you just go around once, you don't cross over yourself, except at the endpoints. Okay, and so I think that does it for these videos.